Okay, so let's start. To welcome to the first lecture in the algorithms. I'm Bhargav, and over the next 6 weeks, I'll be telling you about randomized algorithms. So, you would have already seen the details in the flyers, but today let's first go over the modalities of this lecture series as well as the topics that we'll cover. So, the lecture series will go on till 28th of September, and we'll have two lectures every week on Fridays and Saturdays, and we'll meet from 5 to 6:30 p.m. on both days. So some of you wrote to me and said that you have an issue with this time. So the IEEE folks are going to create a Piazza page or a Moodle page by the end of this week. And so once that's created, we can post on that page and decide on that. Okay. Yeah, so like till that happens, we'll be meeting uh, from 5 to 6:30 on Fridays and Saturdays. But yeah, that situation should be resolved by the end of this week. And towards the end of this course, we'll also have a problem solving and a doubt clearing session, sometimes towards the end. Yeah, so for that, we can decide a mutually convenient time. And so unless there are any questions about modalities, we can tell you the topics that we cover, and then we can start with this week's content. Okay. So, so basically, this course is to sort of give you an introduction on randomized algorithms. So we won't cover too many advanced stuff, but yeah. Hello, were you saying
Yeah,
something?
yes. So
Yeah.
there is some echo is coming. I mean, your voice is not that clear. So I can hear you, but then with lots of noise in the background. But I mean, it's not, you're not clearly audible.
Okay, so I don't know where the noise is coming from.
Not the noise, but then some echo. I mean, your voice is not clear. Probably you can bring
Okay,
your
okay.
microphone closer to your mouth, and then
Yeah,
probably.
so it's this. I can't do anything about it. Yeah, so my okay, uh, okay, but I'm recording from here, so I can't rejoin into it. Okay, let me try this. Is it better now? Hello. Oh, can you hear me?
Yes, I can hear you, but the audio is not that clear. I don't know why.
Yeah. Let's see what I okay, so is it better now?
Yes, you can continue. Maybe some issue is with Teams, or I don't know. Otherwise, on the Google Meet, it used to be perfectly fine.
Yeah. So I'm using Teams because I want to record from within the app. Yeah.
Okay, you can continue, but yeah.
Okay, I can try doing one thing. So the issue is I'm recording from my laptop. So okay, I want to leave and rejoin, but then the recording might end. So okay, okay, I'll go over I need to record the modalities as well. So I'll go over them again. Let's see that if that helps. Is my voice better now?
Yes, yes, it's better.
Okay. Oh, great. The recording did not stop. Yes.
अब क्या करना है मुझे?
Okay. So is it still fine?
Yes, yes, it is fine. In fact, I am also logging in from a different device. Probably then things may
Yeah.
become even better.
Yes. I think what happened was I joined on my iPad first and my laptop later. That was the issue. I should have done it the other way around. So have you reached one?
Yes, yes, I can hear you.
Okay. Okay. Great. Yeah. Okay. So the topics that we'll cover are, so in the first week, we'll just do some basic stuff. So today, most of the time, today we'll just talk about what randomized algorithms are and do a quick review of probability theory. And then I'll mention what Las Vegas and Monte Carlo algorithms are. And tomorrow we'll discuss about them in more detail. Then in the next week, we'll see uh, two randomized algorithms. One of them are Las Vegas algorithm, another Monte Carlo algorithm. And these two are randomized algorithms for quicksort and Kargar's Mincut algorithm. Then in week three, we would see polynomial identity testing and some of its applications like, so I'm thinking of covering the subject protocol, but I'll decide on that in that week. And also in the next week, in the week after that, we'll cover isolation lemma, which is sort of similar to the polynomial identity testing lemma, and also the perfect matching algorithm using isolation lemma by Mulmule, Vazirani, and Vazirani. Then in week five, we'll cover the famous Miller-Rabin primality test, which is used at a lot of places in cryptography to generate large prime numbers. And then we would see randomized approximation algorithms for some of the hard problems like 3SAT, MaxFit, etc. And in the sixth week, I plan on covering Markov chains and their applications to randomized algorithms. However, I'm not sure if I'll be able to do that because some of the content from the first 5 weeks might spill into the sixth week. If that happens, then I won't cover Markov chains. But if everything goes according to plan, then in the next week I'll cover Markov chains as well. So is this fine?
Yes.
Yeah. Okay. So let's start. So first of all, let's define what a randomized algorithm is. But even before that, let's somewhat formalize the definition of an algorithm. So what is an algorithm? It is just a sequence of instructions which are executed one after the other, right? And so an algorithm takes an input, it executes a bunch of instructions on that input and produces an output, right? So once I fix the input of an algorithm, is output becomes fixed, right? And this is sort of the usual notion of algorithms that we encounter in our undergrad and algorithm courses. But there is one more thing that we can let our algorithm do. For example, in real life, you might make like randomized decisions, right? So you can also let your algorithm do something in a randomized way. And that leads us to the definition of a randomized algorithm. So randomized algorithm is an algorithm that has the ability to generate random bits or numbers and use these random numbers or bits during its execution. In particular, the output of a randomized algorithm depends on the random number it uses. And we'll call an algorithm that is not randomized a deterministic algorithm. So, for example, most algorithms that you would have seen till now would have been deterministic algorithms. And here's one toy example of a randomized algorithm. So what the algorithm does is it picks a random number between 1 to 100 and assigns that number to R. Then it checks if the number is 42 or not. And if it is 42, it prints the answer to life, universe, and everything. And otherwise, it just prints some random number. Okay. So the output of this algorithm depends crucially on what the random number picked is, right? If it's 42, it would be this. If it's not 42, it would be this. So unlike a deterministic algorithm whose output is fixed, once you fix the input, in case of a randomized algorithm, the output depends on the random number, right? So just because you have fixed the input does not mean the output is fixed. Is this fine?
Yes.
Yeah. Proceed.
Does this mean that the outcome of a randomized algorithm is can vary? I mean,
Yes, it can vary depending on depending on the random choices of the algorithm. So for example, over here, let's say the number picked was 42, right?
mhm,
Then the output would be this. But if the number picked was 43, the output would be this, right?
yes,
Yeah. So the output crucially depends on the random choices of the algorithm.
yes, yes.
Yeah. So this is sort of one of the main differences between a deterministic algorithm and a randomized algorithm. That in the randomized algorithm, the output need not be fixed just because you have fixed the input. Yeah.
Yes.
Okay. So here's one question. So let A be a deterministic algorithm. Then, and for an input A, I'm denoting by AX the output of A on input X. Okay. So let A be a deterministic algorithm. Then for an input A, X, the output of AX is fixed, right? It
Yes.
cannot change. However, if B is a randomized algorithm, then BX is not fixed, right? It's random. Why is my handwriting so bad? Okay, now it's fit. Yeah. And so what does this output depend on apart from the input?
So it depends on the random number generated.
Right. So the random choices of the algorithm, right? Okay, so instead of not fixed or random, let me write probabilistic. Okay, so since it depends on the random choices of the algorithm, we can say that the output is probabilistic, right? And since the output is probabilistic, we would need, okay, so to analyze randomized algorithms, you would end up needing quite a few facts from probability theory. So you would know most of this, but let's quickly review this. Okay, so we'll start by reviewing a random variable. So over here, I'm giving a very specific definition of a random variable, which we would end up using for this course. This is by no means the most general definition of random variable, but yeah, for the purpose of this course, this definition would be just fine. So a random variable x can take values from a domain x, which is a subset of R, and for all I in the domain, uh, there exists a number pi in 0 to 1. So that probability x equals I is pi, and the sum of all pi's for I in x equals 1. Okay. So strictly speaking, what I've defined over here is called a discrete random variable. But yeah, I'll just call it a random variable. And throughout this course, I'll follow this notation that if the random variable is x, its domain would be script x. And if it's y, it would be script y. If z, then script z, and so on, right? So now let's look at some of the some random variables. So in most cases, what would happen is we would have some random or probabilistic uh, experiment or event, and we would define random variables for it, right? For example, over here we have this experiment of flipping a fair coin, and we want to define a random variable for it. So what's one way to define a random variable for the experiment of flipping a coin?
So, yeah, so x is a random variable and this can take two values, head and tail. So the probability of that x is equal to head is half and the probability of x is equal to tail is also equals to half.
Okay, but this is not a random variable, right? Because a random variable must take values from R, and heads and tails are not in R.
Yes, yes, yes.
So you can just map heads to 1 and tails to 0, right?
Yes.
Yeah.
So
So,
this equal to 1
right.
if the outcome is
Yes. Okay, so now what's the probability of x equals 1? Coin is fair. It's half, right? Similarly, if we were to throw a fair dice, then and want to define the random variable y for it, then what's one way to do this?
this. So for y, I mean the values can vary from say 1 to 6,
Right.
and so but then how to write this thing?
Okay, so y is just equal to the yeah, because over here the outcome itself would be a number, right? 1 to 6.
Yes,
So I can directly use the outcome as the random variable, right?
right. Because
Yeah,
we are assigning a numerical values to the outcome of a random experiment, and that is called a random variable in that sense.
right. So okay, not quite. So you have a random experiment. It might have a few outcomes. Once you map those outcomes to numbers, then you are fine.
Yes,
Then you have a
yes,
random variable.
right.
So for example, in this experiment, the outcome itself was a number. So you can directly use it, right?
Yes,
But over here, the outcome was heads or tails, which is not, these two are not numbers. So you map them to numbers.
yes.
Yeah. So probability y equals to I is 1 over 6 I in, right. Yeah. Okay. So as I said before, the value that a random variable takes depends on the outcome of some random experiment. And for example, over here, for the random variable x, what was the experiment?
The random variable x, the experiment was a pair coin.
Yes, flipping a coin. And for y, it is throwing with a die, right? Okay, so we know that we know about sorry. Yeah, so we have heard about random events, but now let's talk about independent random. Sorry, we have heard about independent random events. Now let's talk about independent random variables. And like throughout the course, quite a few of the random variables that we encounter would end up being independent from each other. So we say that two random variables, x and y, are independent if for all x in x and for all y in y, the probability that x equals x and y equals y is the probability that x equals x times y equals y. So what we are saying is, over here, there are a bunch of events, right? So for all x and all y, this is an event, right? We are saying that all of these events are independent. So is the definition fine?
Yes, yes.
Yeah. And so with every random variable, we have two quantities, uh, its expectation and its variance. And in the analysis of uh, randomized algorithms, both of these quantities play a very crucial role. So let me go over these quickly. So first, I'll define the expectation for random variables. For a random variable x, its expectation is, I'll denote it by this or by this sometimes. So sometimes I'll skip this bracket. So the expected value of x is defined as sum over all small x in the domain, probability of x equals small x times x. So the probability that x is the outcome times the outcome. Okay. And the expectation, which is sometimes also called the expected value, is sort of the average value of x, right? So uh, in the previous page, on the previous page, we saw two random variables, x and y. So what's the expected value of x? How would I do this calculation? So what should I write over here for the set? Script x.
Okay, so for the first experiment, it is x is the element of either the probability of x is equal to so either 0 or 1.
Right. And this is 0 times 1 over 2 plus yeah. And for the second experiment, so what's the set in this case?
Yes, so it is ranging from 1 to 6.
Yeah. So this is
And this is 3.5.
yeah. So this is 6 times 7 over 2, right? So 1, yeah, let me do this here because I have to upload this. Okay, so 1, 3, this is 1, 2, so 7 over 2 is 3. Is this fine?
Yes, yes.
Yeah. Okay, so now let's talk about the variance of a random variable. So the variance of the random variable is defined as the expected value of this random variable. The random variable is x minus expected value of x, the whole square. So first of all, if x is a random variable, now you're convinced that this itself is a random variable?
Yes, but I have a question in the previous
Right.
calculation. So what's the meaning of the term 3.5? Because 3.5 as such is not a valid outcome of the experiment of rolling a dice.
Okay, right. So the expectation need not be a valid outcome.
Mhm.
It's sort of the average value. Okay. So if you were to throw a die, let's say you threw it through. Okay, so here's one way to think of expectation. Suppose you perform an experiment a lot of times. Okay, and
Mhm.
then take the average of the outcome. Okay, so average of the values that the random variable takes. Okay,
Mhm.
that average would be close to the expectation.
Okay.
Yeah. So for example, even over here, half is not a valid outcome, right?
Mhm.
But if you were to toss a coin a lot of times, you would expect to see roughly the same number of heads and tails, right?
Mhm.
And therefore, roughly the same numbers of zeros and ones. So x would take the value zero roughly half of the times, one the value roughly half of the times. And so if you were to take an average, the average would be very close to half, right?
Yes.
Yeah, so this is sort of one way to think about expectation. It's sort of the average value over a lot of trials.
Yes. And what if we take the values as -1 and 1 in flipping a coin instead of taking the values as 1, 0 there?
Right, then the average value would be zero, but the meaning still remains the same, right? Because when you take the value 0 and 1, expectation being half tells you that you got 1 roughly half of the times. That is, you got heads roughly half the time, right?
Mhm.
On the other hand, if you took -1 and 1, the expectation would be 0. But what does expectation being 0 tell you? It tells you that 1 and -1 occurred the same number of times, right?
Yes.
Which again means that heads occurred half of the times and tails occurred half of the times.
Yes.
So even the numeric value is different, the interpretation you get is still the same, right?
Mhm.
For example, in this second case, so how did you define y? We defined y as just the outcome, right? But I could have also defined y as outcome times 10. In that case, y would take place 10, 20, 30, 40, 50, 60, right? And your expectation would be 35, but still the meaning remains the same, right? Because now
Yes.
we are averaging over 20 to 10 to 60.
Mhm.
Yeah.
Right. Right. Yes.
It's much easier to see in this case because it's just there are just two values, but yeah. Yeah, so you are right. The expected value would depend on how you model how you define your random variable for the experiment, the exact values it takes. But the information that you gain from expectation doesn't depend on the exact representation.
Yes.
Yeah. Okay, so yeah. So okay, so now let's come back to the variance. So this is a random variable, right? And so it makes sense to talk about this expectation. Is this fine?
Yes.
Okay. Okay, so I want to derive this, but for that I'm using something that is on the next slide. Okay, so let me get into derivation as much as I can. Okay, so the thing is this is sort of yeah, so this for most of the times, this formula is not the nicest to work with. So we'll try to derive a simpler formula for this. So I can write this square as just okay. Now to simplify this further, I need something I written on the next slide. So let me go to that page. And so that is the concept of linearity of expectation. Okay. So expectation is a linear function. Why? What do I mean by that? If you have two random variables, x and y, okay, notice that over here, they need not be independent. Okay. This works for any two random variables, x and y. And the expectation of x plus y is the sum of the expectations of x and y, so the individual expectation. So I can take this plus out and put the expectation over here. And also for any constant alpha, I should write alpha and yeah, so for any constant alpha, the expected value of alpha times x is the same as alpha times the expected value of x. Is this
Would it,
fine?
yeah, would it be alpha square expected value of x, or
Oh, so there is no square over here.
okay? So I was under the impression that if I multiply a random variable by some amount, and that value gets squared. I mean,
Oh, that's true for the variance.
okay, okay, okay,
Yeah.
okay.
Are we seeing that? Oh, yeah, yeah, yeah. That's the on the next page. Yeah. So we'll look at that. Okay. So now using linearity of expectation, let's try to simplify this. Okay. So how can I simplify this using linearity of expectation? Okay. So what can I write over here? Okay. So what should I write in these brackets?
So following the linearity thing, so this the expectation of the x square would be, so I can write simply x square only, and
Right.
then
So okay.
yeah,
There are three terms over here, right? I can separate all three of them.
yes,
Yeah.
and
So the second one would be uh, this, right? So okay. So over here, uh, there are three terms over here, right? Minus 2x and expected value of x. So out of these, now I want to use this rule to take something common. So what can I take out common? Take outside expectation.
so I mean, uh, I can at the most take -2 out of this thing.
Okay, so minus 2 is a number. I can take that out.
Yes, and
Expected value of x is also a number, right?
yes. So
Yeah,
then,
because
then the
yeah,
expected,
because
yeah,
yeah, I sum over the probability, so all the probability is gone, right?
yes.
Yeah. So I can take that out common as well, right? And over here, what can I write? So what is the expected value of x squared?
So expected of x is also a value then, and then we are taking it
Yeah.
square. So I can take that entire thing out here, and
Yeah. So this entire thing is just a number, right?
yes.
And expected value of a number is just that number because that number is going to be that number with probably one, right?
Mhm.
Yeah. So this is just yeah. And so these two are the same terms, right? So I can write is this fine?
Yes. And the confusion arises here because basically we have not written this expected value of x as mu or by some other symbol. So,
Oh,
so instead of
yes,
this expected of x,
I
if
couldn't
we
hear you properly. Can you repeat?
yes, so because I mean the confusion in the calculation arises because we have not written the expected value of x inside the bracket as by using some other symbol, say mu.
Yeah,
So
yeah.
if I
So
write
yeah,
mu,
I
then the
could have
calculation.
said this is mu, right?
Yeah.
Is this what you're saying?
Yes, yes, yes. So
Yes, yes,
then the calculation would be easier to understand basically. Then
right.
I can easily
Yes.
understand that okay, this is mu and its value is not going to be changed.
Hmm.
Right?
Yeah. Okay. So okay. Remember, recall that x was the random variable, which was 0 with probability half, 1 with probability half, with the one for coin tosses. Okay. So what's the variance for x square x? So I know this value. So expected value of x square x the whole square. This value was half. So this is 1 over 4. But what about the first value?
So so we can compute the expected value of the x square by using that formula. That what
Right.
is the probability of observing the value of x is equal to x and multiplied by the x square. The probability term probably okay, it does not require this thing. Yeah. I think
Okay.
that this, yeah, this x square is equal to x is not required. And instead, we can write that the probability of capital X is equal to the small x. Aren't we?
Okay. Yeah. So that's true, but bad. So, okay, what's your random variable over here? It's x squared, right?
Yes.
And what is the domain of x squared? So the domain of x was 0, 1. So the domain of x squared is also 0, 1, right? Because 0 squared is 0, 1 squared is 1.
Yes.
So if I want to use that definition, what will I have to do? Probability that x squared equals x, because this is the random variable, times the value of the random variable, right?
Yes.
Yeah. But in this case, you can write x equals x because 0 square is 0, 1 square is 1, right?
Okay. Okay. So yeah, but I have a slightly related question that what if instead of the x square, if we have some g of x here, then if I want to compute the expected value of the g of x, then
Yeah. So,
if I want to use the same formula, then
hmm,
would I be writing it as a summation of say the probability of capital X is equal to small x and multiplied by the g of x? I mean, we won't be. I mean, how can this possible that the probability of g of x is equal to the small x?
right. So okay, so in that case, uh, okay, so that's a good question. Let me just add a page and do it. Okay. Okay. Let me do first finish this and then I can talk about it. Okay.
Sure, sure, sure.
Yeah, because otherwise I'll talk about this and then I'll forget about this. So this is so when okay, so when x is 0, this is half times 0, and when x is 1, this is x square is 1, so this is 1, and probability x square is okay. So let me do it like this. Okay, so let me do this slightly more detail. So probability x square is x, right? So what is the probability? So this is so now I have x and I know the probability probability distribution of x, right? So I know which what probability x is 0, with what probability x is 1. So when small x is 0, its square root is 0. So this becomes probability x equals 0, which is half, and x square is 0 plus when small x is 1, the square root of 1 is 1. So this is property x equals 1, which is again half. So this is 1 over 4. Okay, now let's get to your question. So so this is the question, right?
Yes.
Okay, and so first of all, is it clear why the domain of G has to be script x?
So this, I mean, G is a kind of the transformation which we have carried out over the random variable x. So, like say, if I want to compute the expected value of x cube, say,
Hmm.
so then to compute the value of x cube, I was under the impression that it would be that we just need to see that what is the probability of the random variable is equal to x only, and then I multiply it by the x cube. First, I
Oh yeah,
need
so
to
we'll get to that. What I was asking is this fine clear the why G has to be a function from x to R? Why both of these are required?
okay. So what this x here is, which x this is? I mean,
Oh, so
is it
this x is the domain of x. So let me go to the definition of x. Yeah.
okay? Okay. Yes. Yes. Yes.
Yeah. So since G is taking x as input, its domain must be the domain of x, right?
Yes.
And why should the codomain be R? Because
Mhm.
otherwise G of x won't be a random variable, right?
Mhm. Right. Right.
So for example, consider G from 0, comma 1 to tails, comma heads, right? So we mapped head to 1, tails to 0. G does the inverse mapping. G of 0 is tails and G of 1 is heads, right? Now this is not a random variable, so I can't talk about its expectation, right?
Mhm.
That's why the codomain has to be R.
Yes.
Yes. Okay, so one way to do it is this. So yeah, so far we only know how to compute the expected values of like random variables, right? So we need to define a random variable which is equal to gx, right?
Yes.
So now, the domain of pi is just this, right? Is this pi?
Yes.
Yeah, so, okay. Are you convinced that this is the correct expression for the expected value of y?
Yes.
Okay. Now I can do this. So what is y? Uh, what is y? It's g of x, right? So let me put it over here. Is this fine?
Yes, and what this small y here is, this small y is element of this big y.
Can
Okay.
you repeat the question?
So what this small y here is?
Okay, so small y. Okay, so in the definition of expectation, I need to go over all the y's in the domain, right?
Mhm,
So small y is something in the domain.
mhm.
Okay, now let me rewrite this sum as follows. Okay, so what I've done is the following. I have this set y, right? Let me say that y is y1, y2, y3, and y4 to y6. Okay, now suppose that, okay, I need a smaller set. Okay, so let's say y is 1, comma 2. Okay, and suppose that x takes four values, and for x, both x equals to 1 and 2 map to 1, and both x equals 3 and 4 map to 2. Okay, and
Okay.
what I've done is I have divided the set y based on what its preimages are.
Mhm.
So is this fine?
Uh, so actually, I could not understand that why are you using this extra summation here? So now why are we considering this, I mean, for all x, for x, which are the elements of the capital X?
Okay, so for should I include the intermediate step? Okay, so for every y, okay, so for every y in y, I would have some x which is its pre-image, right? So,
Yes.
okay, so what I want to do is, okay, so over here we have this expression gx equals y. From there, I want to go to something of the form x equals something, right?
Yes, yes, yes.
Yeah, so what I'm going to do is I'm going to write down the set y,
Mm-hmm.
and I'm going to pick every value in y and
Mm-hmm.
look at its pre-image in x. Okay,
Mm-hmm.
so let's say y was 1, 2, and both 1 and 2 map to this, and both 3 and 4 map to this, right?
Mm-hmm.
Oh, wait, I wrote the wrong sum. Sorry, the sum is wrong. I did not split it correctly. It's this. So you fix the y,
Yes.
then you sum over all x, such that, oh, sorry, uh, y equals g of x. Yeah, so is it fine now? Over here, I fix the y. Wait, no, something's wrong. This would be larger fit. Fix the y. this shouldn't be g of x equals y. Yeah, sorry. Okay. Okay, so even before that, let me do this. So what is so let's ask this question, and this question would tell us how to split. Okay. So suppose that non-x. Okay, so what am I doing? I have split the set x, script x, into chunks depending on their images, right? So let's say 1, 2, 3, and 4 was x, and 1 and 2 map to 1, and 2 and 3 and 4 map to 2. Then for y equals 1, x1 would be 1, comma 2, and x2 would be 3, comma 4. Is this fine?
Yes.
Okay. Now, my claim is this. Uh, is this claim fine?
Yes, so I'm unable to understand now what this x and this subscript y here is.
Okay, so xy is a subset of the domain of x, right?
Okay.
And
Okay.
what I've done is I have divided the domain of x
Mhm.
into chunks. Everything in x, so xy is one of these chunks, and everything in xy
Yes.
maps to y. So,
Right.
for example, let's say x was 1, 2, 3, and 4, and y was 1, comma 2. Okay. And suppose that, let me just write it. Okay. And now suppose that g of 1 equals g of 2. Okay, so in this case, uh, okay, so what values does y take? 1 and 2, right? So I can think about x1 and I can think about x2. Okay. Now, what is x1? X1 is all the x is in 0 in 1 to 4, so that g of x equals 1. So y over here is 1, right? So for which values of x is g of x 1? For 1 and 2, right?
Yes.
So x1 is the set 1, comma 2.
Mhm.
Similarly, x2 is a set 1, comma, sorry, 3, comma 4.
Three comma.
4.
Yes.
In particular, xy is equal to g inverse y, if you know this notation. This is the pre-image of y.
Mhm.
Yeah, but I'm not using this notation because g might not be an invertible function, right? For example, over here, g is not invertible. It's like this is a set of size 2.
Yes.
That's why I want to avoid this confusion. Okay. Basically, I have partitioned x into chunks, and in each and every chunk, all the values in that chunk map to the same value of y.
Yes.
So a way to pictorially view this would be 1, 2, 3. Everything over here maps to this, everything over here maps to this, and everything over here maps to this.
Yes.
Yeah. And why I would do this would become clear once we look at the entire analysis. Okay. So now I want to claim that probability of that g of x equals y is this value. Let's see why. So when can g of x be y? When x lies inside xy, right?
Mhm.
This set. Because this is the only time g of small x is going to be y,
Yes.
right? So the probability that g of x equals y. Okay, let me write down the reason over here. Yeah. So g of x equals y if and only if x is in xy, right?
Yes.
Yeah. So are you convinced that these two are the same?
Yes. Now I'm convinced. Yeah.
Yeah.
So the
So
only thing
now,
that we are still writing that the probability of capital X is equal to X, but uh, with the reduced value of the X.
yeah, the smaller set.
Yeah. Right.
So now let me put this over here. Okay. And let's see what we get. This is what we get, right?
Yes. Yes.
So now let me take this gy inside. Oh wait, there is no g over here. It's just y, right? It's just y. Yes, sorry about that. So I can take this y inside this smaller sum, right?
Yes.
Okay, so now inside the smaller sum, can you tell me what y is?
So Y is something whose pre-image is there in X.
Right. So, okay, over here, I know that x lies in xy, right? And I also know that y equals g of x,
Yes.
right? So I can simply write this. Is this right?
Yes.
Yeah, because for every x in this set, y has the same value, g
Mhm.
of x, right? X might vary, but y still remains the same.
Yes.
Okay, so now I want to get rid of these two sums. How would I do that? My claim is this is just okay. So how did we define xy? Let me get a picture again. It might be better. So let's say this is x and this is let's say y has just 3 points. Okay. Then I divided X into 3 sets, everything mapped over here, everything mapped over here, and everything mapped over here, right?
Yes.
So now if I look inside this sum, the value of Y is fixed, right?
You were not audible this time. So what did
So
you say? Yeah.
inside this sum, the value of Y is fixed, right? It is this.
Yes.
Yeah, so let's say, okay, so let me first fix the value of Y equals 1. Okay. Then my set XY is this entire set.
Mm-hmm.
If I fix Y equals to 2, it's this entire set. And if I fix Y equals 3, it's this entire set, right?
Oh,
But
yes.
over here, I'm summing over it, right? So I'm going over 1, I'm going over 2, I'm going over 3. So when I'm going over 1, I would have looked at this entire set over here, right? Similarly, when I'm going over 2, I would have looked over at this set. And when I'm going over 3, I would have looked over this set, right? So I'm covering the entire set X.
Right. Yes.
Yeah, so basically, X, Y's form a partition of X, right?
Yes.
So I can combine these two sums as just going over X.
Mm-hmm.
Yeah. So this is what we get. And now if we apply this to the previous problem, then you can see that probability X in 0, 1, sorry, X over X in 0, 1. Probability X is 0 times G of 0 is 0 because it's X squared. And probability X equals 1 times G of X, which is 1 because X squared is 1, right? This is what you were saying.
Yes.
Yes. So is it fine now?
Yes.
Yeah. Okay, so we finished this. Okay, so we also saw linearity of expectation, right? Yeah, so now let's look at this thing. Okay, so we saw that expected value of X plus Y is expected value of X plus expected value of Y. I can take this, like, expectation can distribute over the sum. Now I want to do something like the product, something like that for the product. So I want to say that expected value of X times Y is expected value of X times expected value of Y. Okay, but see, this is not true. Excuse me. Yeah, okay, but this is not true in general. In particular, this is only true when X and Y are independent random variables. Okay, so is the statement fine?
Yes. If X and Y are the independent variables.
Right. So now let's quickly see a proof of this. And okay, one of the reasons I'm showing this is it will become clear why we need this independence criteria because we would end up using this in the proof. So what is this? Okay, how do I want to do this? Directly jump to that, or do I want to first say, okay, let me define a new random variable. Okay, but now I'll do something similar to what I did on the previous slide. Okay, so I skipped a lot of steps over here, but let me quickly try to explain you why this makes sense. So, okay, first of all, this looks something like we did on the previous page, right?
Yes.
Yeah, so what are we doing over here? So you have this large set Z. You know that every element in Z looks like X, Y, right?
Yes.
So what I'm doing is I'm dividing this set. Okay, yeah, let me just draw it because this keeps on disappearing. So we have this set Z and every element in it looks like X times Y, right? So I'm splitting this set into multiple parts. So I'm fixing a value of X, I'm fixing a value of Y. I'm looking at all the elements in Z which are of the form X times Y, right?
Yes.
Yeah, so this is how I'm going to split the set. And once I've split the set, I want to say that, okay, I'll have, okay, so then, okay, let's have split the set. Now let me fix one zx comma y. Let me fix a z, which is in this set, right? So over here, I'm summing. I'm just picking one of the summands where the value of z lies in zx comma y. Okay,
Yes.
for this, the probability that z equals z is the same as the probability that x equals x and y equals y, right?
Yes.
Yeah. So
Can you
I can write.
repeat this statement which you made just now with the
Can you
probability of?
repeat? Can you please say it again?
Yes. So can you repeat this statement which you made just now that the probability of Z is the same as what?
Okay. Okay, wait. Maybe I should write intermediate step.
I could not
Okay.
hear you.
Let me try explaining over here and let me see if I need an intermediate step. Make things clear. So let me fix a z over here. And let's say that z happens to lie in this set zx comma y. Okay,
Yes.
right. So now what's the probability that the value of capital Z equals that small z?
Hmm.
That
So
is x lies in, yeah, so the value of x equals x and the value of y equals y.
right.
Is this fine?
Yes. Yes.
Or maybe I should do this the other way. Anyway, so I fix a z. What's the probability that I get z? Yeah. Okay, so okay, here's another way to think about it. Fix a z. Okay. Now you know that this z must be the form uh, x times y for some x some y, right? Now uh, uh, let's go over all the values of x that give me. Okay, let me go over all the pairs x comma y. Because that their product gives me z. Okay,
Yes.
and the pro so once I've gone over all these pairs, I just need to sum the probability that x is small x, y is small y, because these are all the pairs that give me z, right?
Yes.
Yeah. So is it fine now?
Yes. Yes. That's it.
Yeah. Because let me erase this. This was causing confusion. So basically, I fixed a z, looked at all the xy pairs that would give me that z, and summing over all those xy pairs. Okay.
Hmm.
Yeah. So I got this. Again, look at this. Oh, I'm selecting. Look at this entire sum. Just as before, I can write this sum as Okay, so is it clear why I can do this?
Uh,
So, okay, fix the value of z, then you would have some xy pairs which give you this z, right?
yes.
But if I go over all the values of z, then and I look at the xy pairs that give me these values of z, those would be all the xy pairs, right?
Mhm.
Yeah, okay, maybe a better way of writing this would have been in terms of pairs. So this is a Cartesian product. Yes, is it fine now?
Yes, the only
And
thing
just
is, yeah, what about this? I mean, what about this outer summation symbol? And we are considering all G's, all J's. So yeah, this one.
right. Okay, so so let's forget about this for now. If I had fixed the z, then I would get one partition of x cross y, right?
Yes.
Some xy pairs which give me z.
Mhm.
But if I go over all the z's, then okay, so for every z there would be a set a set of pairs that would give me that z, right? Okay, so for
Yes.
every
So
z, yeah. So if I go over all the values of z and look at the pairs that gave me those values, it would be all the pairs, right? Because fix any pair and take their product. That product would be some z, right?
yes, yes. Now I understood. Yeah.
Yeah. So is the sum fine now? Is it a combination of sum fine now?
Yes.
Yeah. Okay, so then I can write again the same argument. Fix an x, then over here I get all the y's for every value of x, right?
Yes.
Yeah. So now here's here is where I will use independence. Is this fine?
Yes. Because X and Y
Yeah.
are in.
Yeah. And now, so okay, this inner sum is on y, so I can take this out common. Yeah. And now let me throw this bracket as well. So now what is this quantity?
This quantity is expected value of Y.
Yes. Okay.
Yes.
Let me add a page. Okay. Oh, I put it the wrong format. Yeah. And now I can take this expected value of phi out common, right? But this is just the expected value of x. Is this fine?
Yes.
Yeah. Okay, so now, okay. So we have 5 minutes. Okay, so we have 5 minutes. Do I want to do this now or should I do this today, tomorrow for both of these?
Yes, so I think tomorrow would be okay.
Yeah.
I will also go through these notes once again and then yeah, we could.
Yeah, so yeah, a lot of material from today is remaining. Okay, so I'm not sure how much we'll be able to cover tomorrow, but yeah, we'll see. I think, okay, so tomorrow, and you also had some issues with the time, right?
Yes, actually from 5 to 6 there is another IEEE course on computational
Okay,
geometry.
okay.
So it is
So
on Saturday and Friday, and it is having clash on the Friday only.
okay, so on Saturday the time is fine.
Saturday time is fine, yeah, no issues.
Okay, so then one thing we can do is, so I talked to the ISS people. What they're going to do is they're going to create like some Moodle page or a Piazza page. So they will give all the registrants uh, credentials to log into that page. And I think I can also post on that page. So like once that is created, I can ask all the registrants if this time is fine with them.
Okay,
Sorry,
okay,
if a new time is fine with them. Okay,
okay, okay, yeah, no issues.
yeah. I hope that would.
So again, there is some audio issue from your side, and I could not
Yeah,
hear the last part.
that's because so this is running out of battery, so it would like create so it gives you some notification, and that is hard. Let
Sure,
me remove this.
sure, sure.
Yeah.
Sure, sure.
Okay, so yeah, so I was saying that okay, I'm hoping that by this at the end of this week, so by Sunday, they would create that page, and I can ask this question if some new term is fine with everyone. But before that, like, do you have any suggestion for the time?
So yes, so since that class is from 5 to 6,
Okay,
so uh, yeah, and so you can take the class from 6:30 onwards. That would be absolutely fine. Yeah.
okay. So one issue with that is, so right now I'm in my office, and if I leave at 8, I'm not reaching home on time. And
Okay.
if I, yeah,
So again, yeah,
uh,
I could not hear you.
yeah.
There's some disturbance of audio.
Okay,
So
so
so you can take that class say from 6 to 7:30.
yeah,
Yeah.
6 to 7:30 is fine. I should reach reasonably on time. Okay, so okay, I can do this. Let the official time be 6 to 7:30.
Yeah.
But if you are late, maybe you can just email me,
Yes, sure, sure, sure.
and I can start 5 minutes late, or I'll start the first 5 minutes focusing on recap and something like that. Okay,
Sure, 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 sure.
yeah.
That-
Okay, so what? Okay, but before that, when you email, don't email me on my Gmail.
yes.
Email me on my IIS email ID. I'm writing that in the chat. Yeah,
Okay, sure. Sure.
because I see.
Again, I could not hear you, but what I understood is
Yeah,
that whenever I need to write you a mail, then I would be using your ISC email ID because probably
yeah. So
you use this email ID often.
yeah, okay, yeah. So basically, I check this email ID very frequently.
Sure, 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 sure.
Yes,
Great.
every time I get a notification, I check it because it might be important. So yeah, if you reach me, you would reach me quickly. Okay,
Sure, sure. Thank you so much.
Okay, so yeah. Okay. Bye.
Bye. Good night. Yeah. Bye.
All right.